Welcome to 11.1 Inverse Trig Functions. Here we're going to be working with how to find specific numbers and answers off of our initial inverse trig functions. Before we begin, we have to have a full understanding of the properties that are found within all of these inverse trig functions. The very first thing would be that these inverse trig functions must be one-to-one. And that is extremely important because they will have to pass the vertical and horizontal line test. So an equation such as 2x is equal to y. In this exact equation, we're going to end up with specific numbers every single time that we place a y or an x into the value. We will come out with a specific y or x. Let's take a look at the next equation. This part says the equation of the inverse function can be found by replacing x's with y's and y's with x's in the original function, then solving for y. So if we were to have an equation such as y is equal to x plus 3, to find the inverse of it, we would first replace the x and y, and we would once again solve for y. So we would move the 3 over to the left-hand side, and we would end up with x minus 3 is equal to y. Now that y is also replaced with its inverse function, which means y to the negative first power is equal to x minus 3. And another way of writing that would be the f of negative 1 of x is equal to x minus 3. Let's take a look at the next point. The next point states the domain of our function is equal to the range of our inverse. What that means is that as we go ahead and as we have a specific problem, let's say we talk about a point. If a point had 2, 3 as its coordinates, to find the inverse, they would take each other's place within that x or y. So y would go in the place of x, x would go in the place of y. We would then end up with 3, 2. If you take a notice, this main statement of the domain of the f of the function is the range of the inverse, meaning the x takes the place of the y and the y takes the place of the x. In our next point, it says the inverse of f of x is equal to x for every x in the domain of the function and the function's inverse. So every time that we have a function and an inverse function, you will always end up with x being your answer and considering how x is what's inside of the equation. The most important thing is that it has to fall within the range. Last part would be that graphs of f and f inverse are symmetric with respect to the line of y is equal to x. If we take a look at a graph, ultimately, we are talking about that right there being our y is equal to x. In slide 3, we're going to begin by talking about sine. Now we will run through every single one of our trig functions and their inverses. One of the most important things to take a look at within this entire problem or this entire trig function is the domain and the range. Understanding the domain and range is extremely important because we will be using this to help us identify exact values of our answers. Let's go ahead and read that first line. As the graph of sine is the way that it is a wave function, which means that it will not pass the horizontal line test. You can see here on the graph, it runs through multiple points moving from left to right. What will generally happen is that we will narrow down the view. And once we narrow down the view, what would occur is that it now provides an area where this function can pass not only the vertical line test, but the horizontal line test as well. This also allows for us to have a one-to-one function once we've restricted down the graph. The inverse sine function is identical to the sine function, except for the x's have been replaced with the y's, and the y's have been replaced with the x's, meaning our domain and range have switched positions within this graph. If you take a look at the graph itself, you can see that the values were that of the domain of our sine function, and that the range of our original sine function are now in the placement of our x values, meaning our domain. Once again, this is extremely important to note that we have our domain and range here, and it is also important to know that arc sine x is the same as the inverse sine of x. They both have the same equivalent value. As we start working with our sine function, it's extremely important to understand that we will be using a specific side of our entire unit circle. In this case, we are going to be using the right side on the positive and negative side. Let's begin with our first problem. In this problem, we go ahead and identify the inverse sine of 1. So this is extremely important to understand the sides that we're working with. Since we are on the right-hand side, notice we are going to be working and looking for sine being in that 1 position. Now, keep in mind, this will be cosine comma sine whenever we are looking at a point. So this would be 0, 1, 1, 0, and 0, negative 1. Considering how we are looking for sine being in the 1 position, that would point us towards our 90 degrees. Now, our answers are always going to be in the form of radians. So in this case, our answer would be pi over 2. Let's go ahead and take a look at our next problem. In this problem, we have the inverse sine of negative 1/2. Now, it is extremely important for you to know your unit circle. So first thing we're going to do, let's go over the unit circle, make sure that we have a full understanding of every single piece. For our 30-degree angle, that would be a square root of 3 over 2 over 1/2. Our 45 is going to be the square root of 2 over 2 in both the x and y, or the sine and cosine. And our 60-degree angle, which would be 1/2 comma square root of 3 over 2. Now in this case, we are looking for a 1/2 in the sine position. Because of that, we're going to have to realize that the main degree that we are looking at would be our 30-degree angle. Now, Since our 30-degree angle has that 1/2 in the y position, we have to understand, once again, we are not keeping it in degrees, we are using radians. So as we take a look at 30 degrees would be the same as a pi over 6. 45 would be pi over 4, and 60 degrees would be pi over 3. Now, our original problem states a negative 1/2, which means that rather than us looking at the positive pi over 6, we would be looking at a negative pi over 6. And that right there would be our final answer for this problem. In this next slide, we go over the range for each one of our functions, not only the inverse sine, but as well the sine as well. Notice whether we have the inverse on the outside or the inside, our final answer will always be x. And this is the same x that is represented on the inside of our equation. Now, it is extremely important to be able to spot what the range would be, and we are always going to go based off of the outside function. So in this case, the range of an inverse sine would be negative pi over 2, comma pi over 2. And every time that we are working with the sine on the outside, our range would be from -1 to +1. This is extremely important because will tell you whether you are going to be inside of the range or outside of the range. Let's go ahead to slide 8. Here we have sample problems that will help us get a better bearing of how to complete these problems. First thing, we're going to go ahead and take a look at the outside trig function. In this case, we have the inverse of sine, which means that our range is going to go from negative pi over 2 to positive pi over 2. Now, once we go ahead and take a look at our range, we have to figure out, does our x value, the pi over 8, fall within the range? If you're not 100% sure, you find the equivalence of that with the same denominator, which in this case would be a negative 4 pi over 8 and positive 4 pi over 8. In this case, the problem itself, the x, pi over 8, does fall within the max and min of that range, which means our final answer will be the x itself of pi over 8. Let's take a look at the next problem. In this next problem, we have the sine being on the outside, which means that our range is going to go from -1 to 1. We're going to go ahead and take a look at the square root of 3 over 2 and whether that falls within the -1 to 1. One of the easiest numbers for you to realize is that this square root of 3 falls in between the square root of 1 and the square root of 4, which would give us 1 and 2 as an answer. When it is divided by 2, this would leave us with 1/2 or 1. Notice our maximum number is 1, and because we're actually using square root of 3, it would actually be less than our maximum number of 1. In this case, our answer here would be the square root of 3 over 2. Every time that our x value falls within our range, our answer would just be the x. Let's go ahead and take a look at our next problem. Here we have the inverse sine. So in this case, our range is going to be negative pi over 2 to positive pi over 2. Once again, we are going to go ahead and determine whether we fall inside of that range or not. In this case, this would be equivalent to negative 4 pi over 8 to positive 4 pi over 8. If we were to draw out our graph, we would notice that 5 pi over 8 would actually be outside of the area for our sine. Remember, sine is always going to be on the right-hand side, so it will not include quadrant 2 or quadrant 3. Notice in this case, 5 pi over 8 would actually lie between 4 pi over 8 and 8 pi over 8. This line would fall roughly in that location. Since we know that this would be our 5 pi over 8, we're going to find the reference angle, which in this case would be 3 pi over 8. Now, since we are falling outside of the range, we are going to have to find the reflection onto the side, which goes ahead and states that sine would be on that side. In this case, sine is within quadrant 1 and 4. So we're going to take that 3 pi over 8 and find that same angle in quadrant 1. In this case, our answer here would be 3 pi over 8. Now, with this being 3 pi over 8, the main reason why we're doing a reflection over the y-axis is because we are working with sine. So that is extremely important to realize. So 3 pi over 8 is our final answer. Let's take a look at our next question. Here we are working with sine, which means our range would be from negative 1 to 1. Since 0.5 falls between negative 1 to positive 1, our answer here is 0.5. Let's take a look at the next problem. In this problem, we have sine on the outside, which means we're going from a range of negative 1 to 1. And since 1.8 falls outside of our range of negative 1 to positive 1, this answer would actually be no solution. So here we're looking at 3 possibilities of different answers. When it falls within the range, it will always be the x value. If it is larger than the range, but still within the unit circle, we go ahead and we manipulate the reference angle in order to find its true placement within the correct quadrant. And whenever we are completely outside of the range and outside of our unit circle, at that point, our answer would be no solution. Let's go ahead to slide 9. In this example, we are looking at our cosine and our secant function. Most important things to realize would be the domain and range once again. Now, as we shift our graph, notice we are doing the same thing that we did in sine, taking a look at a specific section and having to reduce down every single one of these waved graphs so that they can pass the vertical line test and horizontal line test. It also must be 1-to-1. Now, as we take a look at our inverse cosine, once again, our x's and y's have flipped, meaning the domain and range are now in opposite locations. Keep in mind, a lot of the same properties are still reflected from sine and to cosine. If we take a look at the arc cosine, that still means the inverse of cosine. As we take a look at our next slide, this is helping for us to understand where we would be on the unit circle for our cosine. Notice we're going to be in quadrants 1 and quadrants 2. So in this case, we would go ahead. This would be 1, 0, 0, 1, and negative 1, 0. The right side would be positive, and the left side would be negative. As we begin with our problems for cosine, first thing we're going to do is we're going to take a look at the location of our 0 inverse cosine. Once again, keep in mind, we're going to have cosine as our x and sine as our y. In this case, as we start drawing out our values, notice we have 1, 0, negative 1, 0, 0, negative 1. If we're taking a look at the inverse cosine, that would have to be at our 90-degree angle, which converts to pi over 2. Remember, when the value is given for our x, we are going to go ahead and find the angle in radians. Now, in the case that the angle in radians was given, we would go ahead and find the value. Let's go ahead and take a look at the right side. Here we're being given the inverse cosine of a negative square root of 2 over 2. Now, with us working this problem, the most important thing to realize is that we would be looking for the square root of 2 over 2. As we went over earlier, the square root of 2 over 2 will only be found on a 45-degree angle. Now, since we are working at the negative square root of 2 over 2, in this case, this would have us fall on the left side of our graph, of our unit circle, at a negative. Now, we are thinking in reference to the position of x and y. So this side would be negative, this side would be positive, as we're taking a look at the position and the value of our square root of 2 over 2. When we're looking at the value based off of the angle, what we're looking at is a reference angle of 45, which means that we would be going from the right side to our terminal side, and this would be 135. As we're looking at our 135, we would then have to go ahead and find the angle in radians, which would give us 3 pi over 4. Remember, everything must be done in radians, and you will have to find that proper answer in radians. Let's go ahead and take a look at slide 13. In slide 13, we go ahead and review the range once again. The range for an inverse cosine. would be from 0 to pi. And our cosine range would be from -1 to 1. Now notice for sine and for cosine, they have both been within brackets. They are including those values. That is something extremely important because things will change as we start running into our tangent function. Let's take a look at these sample problems. On the outside, we have an inverse cosine, which gives us 0 to pi as our range. We're going to have to go ahead, take a look at our x. Notice if we were to graph this out, 6 pi over 6, this would be 3 pi over 6. 5 pi over 6 would fall within the area. Remember, for cosine, we are not supposed to be in quadrants 3 or 4. We are supposed to be in quadrants 1 and 2. In this case, we do fall within our range, which means our final answer would be 5 pi over 6. For our cosine, we're once again going to take a look at our range, which would be from -1 to +1. Our value of 1/2 does fall within that range, which means we would go ahead and have 1/2 as our answer. For letter C, once again, we go ahead, take a look at the outside trig function. Our range for that would be from 0 to pi. Once we have done that, we are going to go ahead and graph this out so that we have a better understanding of the positioning of it. This would be our pi, and this would be our 0. Now, considering how we have a denominator of 4, this would actually be 4 pi over 4. Our 90-degree angle would be 2 pi over 4, and our 270 mark would be 6 pi over 4. 5 pi over 4 would fall within quadrant 3. Remember, cosine should not be in quadrants 3 and 4. So what we will do is find the reference angle first, which would be a pi over 4, and we are going to reflect it back into quadrant 2. This would leave us pi over 4 as that reference angle and leave us at 3 pi over 4. 3 pi over 4 would be the final answer for this problem. Let's take a look at our last problem. Here we have cosine. For cosine, remember, we are between -1 and we go up to 1. Now the value of 2 is outside of our range, but we also have to keep in mind the unit circle itself. As we take a look at the unit circle itself, our maximum values fall on the extreme outsides of our x and y, which means 1, 0, -1, 0, 0, 1, and 0, -1. At this case, if we are looking for cosine, which once again, remember that is in the x position, so it's going to fall on our x-axis, 2 would fall outside of our unit circle. Remember, our unit circle would be everything within our graph. Since it's outside of our graph for the number 2, this answer would be no solution. In slide 15, We begin by taking a look at our tangent function, which is one of the last two trig functions that we will take a look at. There are some important things to keep in mind as we take a look at this graph. First would be the domain and range, but it would also be important to take a look that we are having parentheses around our domain and our range. It's common for the range to have parentheses because we are going from negative infinity to positive infinity. But it's also important that we take a look at the domain. The fact that we have asymptotes going vertically through our x-axis causes us to not be able to include the negative pi over 2 or the pi over 2. Everything within that range would be perfectly fine, but we cannot use those values. Once again, we cannot use the negative 1 pi over 2 and positive pi over 2, so we must use parentheses. In our inverse tangent, it is extremely similar because what happens is the domain and the range flip, and now the inverse position would be taken. Once again, arctan is the same as the inverse of tangent. Let's go ahead and take a look at slide 17. In this case, this problem is very similar, or this trig function is very similar to that of sine. We will be looking at the right-hand side, but one key indicator that we are looking at tangent is that we have holes at both negative pi over 2 and positive pi over 2. Remember, we have asymptotes that run along that value, which means we cannot include it. That would be the main reason for there being a hole at the pi over 2 and negative pi over 2. In our next slide, we're going to go ahead and work on a couple sample problems. First thing to understand is that anytime that we are dealing with tangent, tangent is equal to sine over cosine. The inverse tangent would actually be cosine over sine. So we're going to go ahead. We're going to take a look at our first problem. In this case, we have the inverse tangent of 1. With this problem, we have to determine what would give us an answer of 1 when we are dividing our cosine by our sine. The values must be the same, which means that we have to be looking at a 45-degree angle of some type. In this case, our square root of 2 over 2 is being divided by the square root of 2 over 2 to provide us with our answer of 1. The next question would be, is this 1 positive or negative? Because this is a positive 1, this would be falling within the first quadrant. Our answer here would be pi over 4. Let's take a look at our second sample problem. We have the inverse tangent of a negative square root of 3. Keep in mind, if we are working with the inverse tangent, this means that we're really going to be taking a look at our cosine being divided by our sine. Now, in order for that to happen, we have to take a look at the values that we would end up with. To place a square root of 3, the only location that we would have would be the square root of 3 divided by 2 being divided by our sine. And notice, since we do not have a denominator, our denominator must have been canceled out, which means this would be a 1 over 2 value that it was being divided by. Remember, this would be our cosine, and this would be our sine. We have to determine where our cosine for a square root of 3 over 2 would be. And in this case, this would leave us with the square root of 3 over 2 times 2 over 1. Our 2's go ahead and simplify and leave us with the square root of 3. Most important thing that we're going to do is have an understanding of where we would have cosine be a square root of 3 over 2 and also end up with a 1/2 as well. In order for cosine to be square root of 3 over 2, we would be looking at one of two things. We would either be looking at a positive 30 degrees or a negative 30 degrees. We would have to follow the negative 30-degree angle because keep in mind, first, we have a negative in this problem, and the only way we can end up with a negative is if one of our two values is negative. For a 30-degree angle, both would be positive, and for our 30-degree angle, or negative 30-degree angle, we would have a positive negative. In this case, this would mean that our problem would be at a negative pi over 3. Let's go ahead and take a look at our slide 19. Once again, we go over the same exact instructions that we did with sine and cosine. We take a look at the outside trig function. In this case, since we have the inverse tangent on the outside, this means that we're going to have a range of negative pi over 2 up to pi over 2. Now remember, this is not going to include those values, so we're going to have parentheses around them. And for tangent, we're going to go from negative infinity to positive infinity. Once again, with parentheses around them. In the sample problems we are going to be working on, we would repeat the exact same process that we have been doing up to this point. First, we write down the range that we are looking at. In this case, the range for negative, or for an inverse tangent, would be a pi over 2, positive negative with our parentheses. Since pi over 6 does fall within those values, we would go ahead and have our answer of pi over 6. Now, just in case, remember, what you can always do is go ahead and find an equivalent fraction of negative 3 pi over 6 for each and determine whether it falls within. Let's take a look at arctan. Now remember, arctan is the same as the tangent inverse, which would be negative pi over 2 to positive pi over 2. Now, in this case, what ends up happening is we are going ahead and graphing it. Now, since we're looking at 2 pi over 3, 2 pi over 3 would actually fall within quadrant 2. Remember, tangent is similar to sine, which means tangent would be wanted in our first and fourth quadrants. We would not want it in quadrants 2 or 3. Because of this, even though we are at 2 pi over 3, we would have to find the reference angle, which would be pi over 3, and we would reflect it over the origin into quadrant 4. So this pi over 3. Now keep in mind, if we are looking at a reference angle of pi over 3, this location would exactly be a negative pi over 3. And that would be our answer. Negative pi over 3. So once again, anytime that you have a tangent trig function or inverse tangent trig function, you would be doing a reflection over the origin. Let's take a look at C. Here we have tangent being on the outside, which means we are going from negative infinity to positive infinity. Considering how this includes all numbers, our final answer would be the square root of 3. The same thing would be happening for D. We're going from negative infinity to positive infinity. Notice, since that falls within, or since the number negative 4.2 falls within a negative infinity to positive infinity, this will be our final answer of negative 4.2. Our last slide, slide 21, goes over a summary of the domains and the ranges for our inverse trig functions. Something to keep in mind as we're doing our reflections. Our reflections would occur for sine from left to right. So if we ended up in the second quadrant, we would reflect over the y-axis and into its appropriate quadrant on the right-hand side. So the reflection is over the y-axis. When we're taking a look at the inverse cosine, in this case, if we ended up in a third quadrant, we would have to reflect over the x-axis and into the second quadrant. And the last would be the inverse of tangent. If we are reflecting for the inverse of tangent, if we are in quadrant 2, we would go ahead and reflect over the origin and into quadrant 4. Now, this would happen at any point for each of these different inverse trig functions. The same thing can occur, let's say in sine, inverse sine, if we were in quadrant 3, it would reflect to quadrant 4. If we're in quadrant 4, we would reflect to quadrant 1. And for tangent, if we were in quadrant 3, it would reflect over the origin and into quadrant 1. Hopefully this provides you with a better understanding of inverse trig functions.